Greetings, AP Chemistry. This is Mr. Harper. I hope you guys are having a good vacation and a good break from school. Today we're going to talk about here kind of for a little while is intermolecular forces and the effects they have on liquids and phase changes of matter. So, yeah, here we go. So real quick, just to review from the other day, we said that intermolecular forces and their strength affects the properties of liquids, or they affect the properties of liquids, okay? The properties that they affect include, but are not limited to, boiling point, melting point, surface tension, viscosity, and critical temperature. We are going to focus on boiling point and a few of these others today here in the lecture, but I strongly recommend that you read in your book section 13.2. It's an easy read, it's a fast read, and that'll tell you about surface tension and viscosity, which we're not going to talk too much about today because they're less relevant, and it's much more important to understand boiling point, and also, I forgot to write down on here, heat of vaporization, okay, very closely related. So, before we take a look at some pictures and talk about vapor pressure, oh, that's another one. That's another good one. Another one it affects is vapor pressure. Okay, before we look at these things here today in the lecture, we have to get some vocabulary down. When we are talking about phase changes, okay, these three words are often used to mean the same thing, but they are not the same thing. When we say vaporize, what we are saying specifically is that a liquid is changing into a gas. We know that, but it is happening at the boiling point. So the boiling point, if we just define boiling point here really quick, the boiling point of a liquid is where the vapor pressure exerted by the liquid is equal to the atmospheric pressure. Now you're going to ask me, oh, Mr. Harper, what is vapor pressure exactly? Well, we're going to talk about that, okay? But that has a specific definition, okay? The boiling point is a specific temperature at which the vapor pressure exerted by the liquid is equal to the external atmospheric pressure. That's vaporization. Evaporation of a liquid occurs when the gas has a temperature below the boiling point. So here the temperature is less than the normal boiling point of the liquid. And we're going to talk about why this happens as well. Okay? At any temperature, a liquid can vaporize. We'll talk about the reasons for that. And lastly, boiling. Okay, boiling is where like we just said, is where something is changing, is vaporizing, changing from a liquid to a gas. Where and the condition here is that the vapor pressure of the liquid that's exerted by the liquid is equal to the atmospheric pressure. This happens at the boiling point, obviously. Okay, so boiling is the process, or is the, you know, I guess you could just say you could say a liquid is boiling when it is vaporizing. So these two terms are sort of related. So keep in your mind the difference between those things. All right. So when we talk about vaporization, okay, or any transition of something from a liquid phase into the gaseous phase, this is what is happening. Imagine, if you can, a sample of good old dihydrogen monoxide, H2O. And down here on the bottom, as the diagram suggests, is you have this stuff down here is in the liquid state. Now, what defines the liquid state is that the molecules are packed relatively close together, and they are experiencing intermolecular attractions between the water molecules. So those molecules are attracted to each other. Those molecules are attracted to each other. That one's attracted, well, to that part of the molecule right there, and this is attracted to that one. And all these molecules that are packed closely together into the condensed phase are experiencing intermolecular attraction. Now, if I ask you guys what kind, or what is the strongest type of intermolecular force that is attracting water molecules together, you would tell me, of course, well, Mr. Harper, these are experiencing hydrogen bonding. Okay, so that is what is holding these molecules together into the liquid phase, that attraction. Okay. Now, in order for molecules of water to go from the liquid phase into the gas phase, which is what this one right here is doing, okay, what has to happen is that the molecules have to have enough kinetic energy to escape the liquid phase. Or in other words, basically what's happening, if you consider just this molecule right here, this molecule is being attracted to its neighbors through hydrogen bonding. In order for that molecule to get away and move into the gas phase, it has to have enough energy to break free from that attraction that is holding it into the liquid phase. Okay? Now, like we talked about the other day, the stronger the attraction is between molecules. Okay, so the more that this guy here is held, the more tightly it is held by the other molecules, the stronger the intermolecular force of attraction between that and other molecules are, the more energy it takes to break the interactions, or the intermolecular forces of attraction that are acting between molecules. In this case, it's hydrogen bonding. That takes, relatively speaking, a lot of energy to break. Okay? Now, let's take a look here at a picture. These are two graphs, and what these are showing is a distribution of kinetic energies had by molecules in a liquid sample. So here on the y-axis you have the number of molecules with a given potential or with a given kinetic energy. On here on the x-axis you have the kinetic energy. Now, assume for a second that we're at temperature 1. Temperature 1 could be any temperature. Maybe, let's just say, just for the sake of argument, it is, I don't know, room temperature 25 degrees Celsius. Okay. Here's the distribution of kinetic energy that is had by molecules in a sample. If we just pretend for a second that this is a sample of water, okay, what this shaded area here represents, or what this line here represents, rather, is the minimum energy that's needed to overcome intermolecular forces in the liquid. In other words, this is the minimum amount of energy that it requires for a molecule to escape, okay, from the liquid phase and go from a liquid to a gas. Okay. Now, if we look here at the distribution of energies had by the molecules, you will notice that at room temperature, if we're saying this is water at room temperature, there is a certain fraction of those that possess, okay, enough energy to escape from the liquid phase and enter into the gas phase. They have enough kinetic energy to break free of the hydrogen bonds that are holding it into the gas phase. So, if we consider back this picture we looked at before, some of these molecules here in the sample, maybe it's that one, who knows, or maybe it's this one right here, okay? Maybe those molecules have enough kinetic energy to where they can break free of the liquid phase and enter into the gas phase. So they have enough natural kinetic energy at that temperature to escape into the gas phase and break the hydrogen bonds, basically, okay? Even at low temperatures, this is going to be true. Some molecules will have enough energy to do that. That is why things evaporate, okay? Because we know at 25 degrees Celsius, this is way below the boiling point of water. We know water boils at 100 degrees Celsius, okay? Where the fraction of molecules having sufficient kinetic energy to escape into the gas phase is going to be much, much, much higher. But even at low temperatures, there are some molecules, not very many, but there are some at any given point in time that have enough energy to go into the gas phase, and that is why liquids will evaporate. It's kind of a random process, okay? So it's due to the fraction of the molecules that have enough energy to escape into the gas phase. Now, when we raise the temperature, say we take T1 and we change it to T2. Let's just say for the sake of argument, the T2 would be 50 degrees Celsius. I don't know what it is. It's just, we'll say it's a higher temperature. Okay, now you notice what happened here to the distribution. If we look at the kinetic energies of the molecules in the sample, the distribution has changed shape. The minimum energy it takes to escape into the gas phase is still the same. This point has not changed. But what has changed here about our graph is the fraction of all molecules with enough kinetic energy to escape into the gas phase. You notice that as the temperature goes up, and on average our molecules, we know if we think about the motion of the molecules at a higher temperature, they'll be moving around much, 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 much faster. So if we add energy, they're going, wee, okay, flying around way faster. When they do that, when we raise the temperature, the average temperature, a greater fraction of molecules will have sufficient energy to enter into the gas phase to break those intermolecular hydrogen bonds. Now, and that is kind of the point, guys. As we go through and we discuss how things are going into the gas phase, that is the necessary condition for things to enter into the gas phase. They have to have enough kinetic energy to break the intermolecular forces of attraction holding them in the condensed phases. And the greater the temperature that the sample is at, the more molecules at any given time will have enough energy to do that. Okay? So, some time ago, if we think back to chapter 6, we looked at something like this. This is a graph that's called a heating curve. Okay? So, remember we started down here with, you know, if we consider this is for H2O, this heating curve here is made for water. We can start down here at the bottom with a sample of ice, and then if we apply heat we see the temperature goes up, and then we get here to point B, which is the normal melting point of ice, and then the ice melts, and then we get to point C, and then from point C to D, we see the temperature is changing, and then from D to E over here, okay, then the temperature is staying constant as the water it vaporizes, etc. We've looked at heating curves like this before. Let me explain to you why this graph is the shape that it is in light of what we just talked about, okay? If you look at this region right here, kind of, we could say, step 1, okay? When your ice is heating up from a very low temperature, in this case on the graph, negative 25 degrees Celsius up to 0 degrees Celsius. On that range of the heating curve that we looked at before, we saw that the temperature changes. Now, the reason why the temperature is changing is as you supply energy, what that energy is doing is it is making the molecules move around faster. It is changing the distribution of kinetic energy, like we saw in the previous graph, okay, of the molecules in that sample. You're raising the fraction of them that have enough kinetic energy to escape into the next phase, okay? Over this range right here, between B and C, you could say region 2 here on the graph, what is happening there is as you heat it, we see the temperature is not changing. The reason why is there, the average kinetic energy of the sample of water, in this case, stays the same. What is happening is that the extra energy that you supply is being used to break hydrogen bonds that are holding the sample into the solid phase. Because keep in mind, guys, the main difference between the solid and the liquid is the number of hydrogen bonds that are forming between molecules. In the solid phase down here, okay, where the molecules have the low kinetic energy, okay, they don't have enough kinetic energy, many of them, to escape the hydrogen bonds, and so they're locked into place. That's what makes a solid form, okay? If we look here at the next range of the graph, skipping around, if we look over here from going from C to D, again we see the temperature changes. What that corresponds to is a change in the average kinetic energy of the sample of water molecules that we have. So there, we're changing the distribution of kinetic energies, and more and more and more and more and more of them are having enough kinetic energy to escape into the gas phase. And in a similar fashion here, when we go from D to E, this is the, where the water is boiling, okay? And we're changing liquid water into gaseous water at a very fast rate, okay? What is happening there is as you go across this region of the curve, okay, like we've seen before, you are, the energy supply is breaking the intermolecular hydrogen bonds and causing the water molecules to enter into the gas phase. Now, recall we said before, because you're going to do some calculations, this is kind of a throwback to Chapter 6, you're going to do some calculations tonight involving phase changes. To calculate something where ice is, where we're changing temperatures, so region 1 or region 3, to calculate delta H, the heat required for that step is going to be M times C times delta T. If we look at something when it is boiling, the heat change associated with that step is the mass of the water times the heat of vaporization. And down here, when it is melting, to find delta H is equal to the mass times the heat of fusion, where the heat of vaporization and the heat of fusion are the amount of energy needed to vaporize or to melt a sample of water, in this case, respectively. Okay? Now, if we take a look at this energy here, the heat of fusion compared to the heat of vaporization, what you're going to notice for most substances is that there is a dramatic difference. If we compare them here, which is what's on the next slide, okay, you're going to see here, okay, so let me explain this graph. If we look at butane right here, the part of the graph that's here in green represents the amount of energy it takes to vaporize a sample. So that's the heat of vaporization, and then in kilojoules per mole, and then the red part here is the heat of fusion. So this is the energy needed to melt something. And if we compare the heat of fusion, the heat of vaporization for butane, and for diethyl ether, and for water, and for mercury, you're going to notice that, generally speaking, the heat of vaporization, the amount of energy it takes to vaporize things and put them into the gas phase, is much higher than the heat of fusion, which is the amount of energy needed to melt something. Okay? Now, here's the reason why. When something goes through a change of state, what is really changing? You're not breaking any of the chemical bonds within the molecule. So, for example, if we vaporize H2O, Okay, and this is a common question on the AP test, and it's remarkable how many people get it wrong. If you take liquid water and we put it into the gas phase, we boil it, say, it just changes from H2O liquid to H2O gas. The identity of the molecule does not change. We're not breaking any chemical bonds. What you are breaking is the intermolecular attractions between the molecules. In this case, hydrogen bonds. You must break the hydrogen bonds holding water molecules to each other in order to cause a change of state. When you go from a solid to a liquid, okay, you have to break some hydrogen bonds to allow the molecules to move about to grant them some degree of freedom. The difference, though, is when you go from the liquid phase into the gaseous phase, at that point you have to break all, okay, or every intermolecular bond or force or attraction or whatever, however you want to say it. When you go from the liquid phase into the gas phase, you have to destroy every intermolecular attraction that holds the molecules together. That is why this takes so much more energy than this, is because here you're only breaking some of the intermolecular force attraction, whereas here you've got to destroy them all, and that takes, as you would imagine, a lot more energy. The reason why is to go from, that's the defining characteristic of the gas phase. The molecules are totally separate, they're moving around very quickly, and they're not, while they do experience attraction to each other, the force of that attraction is not sufficient to slow them down and bind them together. So that is why, guys, it takes so much more energy to vaporize something than to cause it to melt. Okay, so that's some information there about heat of vaporization. Let's switch gears here and talk about something which is related. Another property of a liquid that we're going to look at here today is something called vapor pressure. This is related to vaporization. As you would imagine, as the name implies, this is also related to vaporization. Okay. Consider these flasks right here, okay? If we take, we'll just, again, we'll use our example of water. If we take our sample of water, like we said before, if we just take some water here and we put it into our flask and then we seal it, let's think about what's going to happen physically. If we go all the way back here, let's go back to slide, okay? If we take a look at this picture, like we said before, a sample of water at any given temperature is going to have, the molecules will have a distribution of kinetic energies. Most of these molecules here are going to stay into the liquid phase, but at any temperature, there's going to be some of these which has sufficient kinetic energy to escape the liquid phase and enter into the gas phase. Okay, so this is a dynamic process that is going to be happening all the time, okay, for any sample of a liquid at different rates depending on the temperature. Okay, now if you think about that, we just take some water, we put it in a flask, and we seal it. Okay, some of these molecules are going to vaporize, they're going to enter into the gas phase. Now, when they do that, they exert a pressure on their container. We have these gas molecules here that are flying around once they vaporize, and they run into the sides of their container. Okay, when they run into the sides of their container, they exert a pressure. That pressure that they exert is called vapor pressure. You might just want to write that down and define that really fast. Okay. Now, what's going to happen? Okay, at first it doesn't exert very much vapor pressure, but as it goes on, eventually what's going to happen is you're going to have some of these molecules are going to be vaporized into the gas phase, and it's going to stop happening when molecules, in this case of water, are entering the gas phase at the same rate as molecules in the gas phase are going back into the liquid phase, because both processes are going to happen. You have some of these molecules that go into the gas phase, and then once they're in the gas phase, some of these molecules up here lose enough kinetic energy to where they can go back and return into the liquid phase. Okay, so once they've reached this point where those two processes are happening at the same rate, guys, this is called equilibrium. We have got whole chapters on equilibrium in next semester. We talk about chemical equilibrium, but know that what equilibrium is, guys, is a state in which the forward and the reverse process are happening at the same rate. When this achieves equilibrium, by the way, guys, at first, some of this water is going to evaporate. You'll notice here the level of the liquid is higher than in this flask right here. Okay, because some of the water has evaporated and changed into the gas phase. Once equilibrium has been reached, okay, the level of the liquid is not going to change anymore. And then if we measured the pressure exerted by the gas mixture here, that would be called the equilibrium vapor pressure of the liquid. I'm just going to say P vap, P standing for pressure, and vape standing for vapor pressure. Okay. Now you might ask me, Mr. Harper, how do we measure vapor pressure? Well, I'm glad you asked. There are a variety of ways to do it. One is with a barometer. If we can advance computer, go to the next slide. Thinking about it, there we go, okay. If we want to measure vapor pressure, what we use is something called a barometer. These are pictures of a barometer, okay? One way you could do this is using a reference. So this leftmost barometer here is just normal. And how a barometer works is this is a glass tube, okay? And it's put down into a pool of mercury, and all the air is sucked out of it. So here at the top, what you have is vacuum. There's nothing in there. When this evacuated tube is put into a pool of mercury, what's happening is that the air, okay, around us is pushing down on this pool of mercury, and it forces some of the mercury up into the barometer. We can measure the height of the column of mercury and figure out how much pressure is being exerted from the height of that column of mercury. Now, you may have in the past seen a measurement of pressure that looks like this. This might be 760 millimeters of mercury. Well, guys, millimeters of mercury is just the height of that mercury column here in the barometer. And so this is also equivalent to 760 torr, or you could also call this 1 atmosphere of pressure. That is the normal atmospheric pressure. So this is a normal barometer with nothing inside. One way you can measure the vapor pressure exerted by a substance is to take a normal barometer like this and inject into the top here a sample of your liquid that you want to measure the vapor pressure of. So in this case, we're doing this for water vapor. We can inject some water up there, and then what that's going to do is it's going to press down this column of mercury somewhat. Okay, so you have the air pressing it down and pressing it up, okay, so that's what the air is doing, and then you have the vapor pressure from the water, in this case, pressing that down. And the more vapor pressure that this liquid exerts up here, okay, the more this is going to be pressed down. Okay, that makes sense. So we can look at the difference in the reading here. I'll maybe use another color here. Okay, we look at the difference between what we read here and what we read here to figure out the vapor pressure. So in this case, the vapor pressure being exerted by the water is 24 torr because it's pushing this down. In this case, we can read the vapor pressure. This is of, this right here is ethanol. Here has been injected here into the top. We can measure the vapor pressure here exerted by the ethanol. There is 65 torr. And here for, this is diethyl ether. This thing right here is diethyl ether, a fabulous nonpolar organic solvent. Okay, and you can see this is exerting a whole lot more vapor pressure right there, 545 torr. Now, vapor pressure a lot of times is used to measure something called volatility, which is basically telling you volatility. It basically tells you how easily something evaporates. The higher the vapor pressure something exerts, the more easily it evaporates. And if it evaporates very easily, we say that it is volatile. Water, as you can see, is not very volatile. Ethanol is somewhat more volatile, but diethyl ether is real volatile. Now, here's why that can be a problem sometimes. Diethyl ether is a fabulous solvent that is used in chemistry labs all over the country, but it is also used by street chemists out there to make methamphetamine as a solvent during part of the extraction process. I won't give you more details on that, but if you ever see on the news that some house burns down that had a meth lab in, odds are strong that it's because they're using diethyl ether. Diethyl ether, if you leave the container open, will vaporize, and it will do that very rapidly and can fill the room very quickly with extremely flammable vapors. And when you spark a match, or when any kind of spark goes off, you can ignite those fumes and cause wherever you are at to burn down. It also burns with an invisible flame, and so it is really, 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 really dangerous. We don't use it in AP Chem Lab, although when you go to college, you will. Okay, so enough on diethyl ether. Okay. All right. So there's vapor pressure. That is what vapor pressure is. So vapor pressure relates to boiling, as you can probably imagine. When we, at the very beginning of the lecture, we said we're going to be talking about boiling points and how intermolecular forces affect boiling points. Well, when something boils, when a liquid boils, okay, that occurs where the atmospheric pressure equals the vapor pressure exerted by the liquid. Okay, if we go back, Okay. To slide 8, if we go back, okay, there we go. We said that every liquid exerts a vapor pressure that comes from molecules that are in the liquid phase entering into the gaseous phase. Okay. Well, the higher the temperature that a liquid is at, the more this is going to happen. So we raise the temperature on this liquid, more of these molecules are going to be entering into the gas phase. When you have more molecules entering the gas phase, as you can imagine, they're going to be hitting the walls of their container more, and they're going to exert a greater amount of pressure. So as you raise the temperature, more molecules go into the gas phase, they exert more pressure, and finally, when the vapor pressure exerted by the liquid is equal to the atmospheric pressure, that is when a liquid boils. Okay, so there we go. And this temperature at which that occurs depends on the pressure, depends on the atmospheric pressure. Generally speaking, the boiling point increases as the pressure goes up. So we have to define the boiling point in terms of both temperature and pressure. So if we say ever normal boiling point, if we look at the normal boiling point of a liquid, what that is it's the temperature that a liquid is going to boil at when the pressure, when the pressure is equal to 760 millimeters of mercury, which is also the same thing as 1 atmosphere pressure. That is what the normal boiling point is. Now, if we look at a few liquids right here, if we look at diethyl ether, and we look at ethanol, and we look at water, here is for each of these things their normal boiling point. So at diethyl ether, the normal boiling point is 34.6 degrees Celsius. Ethanol, the normal boiling point is 78.3 degrees Celsius, and water, the normal boiling point is 100 degrees Celsius. If I were to ask you guys which of these is the most volatile, well, you would say that, well, Mr. Harper, that would be diethyl ether, because if we look at any temperature below 100, below, whatever. Say we look at a temperature of 20 degrees Celsius, and we compare the vapor pressures exerted by these three liquids, the vapor pressure exerted by diethyl ether is the highest. You might be able to estimate that that's going to be somewhere in the area of, I don't know, 450 torr or something like that. If we do the same thing at 20 degrees Celsius for ethanol, it's going to be down here, something like maybe 50 torr. And water would be even lower, like almost nothing. So we can see here clearly that diethyl ether is the most volatile of these liquids. Now, if I was going to ask another question, which of these three liquids has the weakest intermolecular forces? If we go back here and look at the graph, which of these does have the weakest intermolecular forces? We can answer that by drawing the Lewis structure, but we can also rationalize that just by looking at their boiling points and the vapor pressure that they exert. Generally speaking, guys, the higher the vapor pressure something exerts, the easier it is for molecules of that substance to break free of the liquid phase and enter into the gas phase. The easier it is for them to do that, the weaker or the less strongly they're held together, and so the weaker the intermolecular forces of attraction. So if we wanted to rank these liquids here in order of increasing magnitude of intermolecular forces of attraction, diethyl ether, has the weakest intermolecular forces of attraction. It has the lowest boiling point and is the most volatile liquid, so the more volatile it is, the weaker the intermolecular force of attraction. This is less than ethanol, which is less than good old H2O. H2O of these three is going to have the strongest intermolecular forces of attraction. Question number 2: at what temperature does water have a boiling point, or have a vapor pressure of 600 torr? If we look back here at the graph, 600 torr is going to be right about here, and if we look at the temperature at which water will have that, we trace on down here, and that'll be, I don't know, maybe about 93 degrees Celsius or something of that nature. Because we see that the vapor pressure that the water exerts depends on the temperature. The higher the temperature, the more vapor pressure it is going to exert. And question number 3: what are 2 ways to get a liquid to boil? To answer this question, let's take a look back here at the graph, guys. 2 ways to get a liquid to boil. We said that for something to boil, the atmospheric pressure okay, it has to be equal to the vapor pressure. There's two ways to get that to happen. One would be to leave the pressure, the applied atmospheric pressure constant, and to raise the temperature of the substance. So, for example, if we consider water, let's look at this blue curve right here. If we leave the atmospheric pressure at 760 torr, okay, we can just raise the temperature of the water in order to get it to boil. So if we raise the temperature, its vapor pressure goes up, 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 until it hits 760 torr. At this point, okay, then this is going to boil. So that is one way we could cause something to boil. There's another way you can make the atmospheric pressure equal the vapor pressure. And that would be if you reduce the atmospheric pressure. If we somehow were to reduce the pressure on the system, say we did it to 400 torr, say we reduced the pressure of the system down to 400 torr, and then we find the boiling point. You can see the boiling point there of the water, it would be much lower. It would be substantially lower. It would be at 80 degrees Celsius, which I know you might say that's not that much of a change, but for practical lab stuff, that really is. So you can, by reducing the pressure on the system, you also change the boiling point and can get it to go down. So there you have. Well, that was weird. Okay. Now here's an application of that. Now, when I was young, I wanted to be an astronaut, and something you guys know about. Well, I don't know. I wanted to be a paleontologist first, but and then for about a week, I wanted to be an astronaut, and then I saw Apollo 13, and that changed my mind. But as you guys know, when you go out into space, if you ever get to be on a space shuttle, when you go out into space and you walk out here to do some work on the International Space Station or something of that nature, you have to wear a complex spacesuit. Now, the reason for that is two things. Number one, to keep your temperature at some sort of reasonable level because space is not very warm. But the other reason is to keep the pressure, the applied pressure on you high, because out there in space, the atmospheric pressure is about 0. If the atmospheric pressure is about 0, what that means is that since you are mostly water, you are going to boil. So the purpose of a spacesuit when you go out into space is to keep the pressure around the atmospheric pressure so that the fluids in your body do not turn into a vapor and you do not explode. All right. One last thing, guys, and we are going to call it a day here for the podcasting. I just want to review with you one thing really quick from last year, and this is a type of graph called a phase diagram. What a phase diagram tells you for a substance is the relationship between the three phases of matter for that substance at different combinations of temperature and pressure, because we've seen that the phase something is in, predominantly, whether it is a liquid, a solid, or a gas, depends on the temperature that it is at, okay? So this is how it works. It's always going to, well, usually will have some sort of a Y shape. Now, there are ones that are more complicated for different substances that have more than one solid phase, but we'll talk about those later. Okay, it's usually some sort of a Y shape like this, okay? And along this line right here, what you have is the combinations of temperature and pressure in which the solid and liquid phases are at equilibrium. So along this line, you have solid and liquid. And what you have happening at the same rate is things melting and going to a liquid and freezing and going to a solid at the same rate. In this region over here of the graph, you're going to have just the solid phase. In this region, at combinations of temperature and pressure that are over here, you have gas, and down here in the middle, at combinations of temperature and pressure that are in this range, you will have just the liquid. In the same way, along this line here, you're going to have the equilibrium point between the liquid going back and forth to the gas at the same rate. That is called the boiling point. So along this line, these combinations of temperature and pressure is where you're going to see a liquid boil. And then along this line down here is where you're going to see the solid going back and forth to a gas. That process is called sublimation. And the best example of something that sublimes is dry ice. I don't know if you guys ever play with dry ice, but dry ice is solid carbon dioxide. When you take that out of the freezer, it goes directly from a solid into a gas. Okay. Now, that's how you read this graph. So what these are useful for is if you have some substance and you want to know, well, is it going to be a solid, a liquid, or a gas at this temperature and this pressure, you can just look at, the graph and say, oh, it's over here, okay, so it must be a solid, or it's over here, it must be liquid, or it's over here, it must be a gas, or maybe it's right here and it's boiling, or it's right here and it's freezing, or it's down here and it's subliming. There's a couple of special points here that you need to take note of. One is right here. This is called the triple point. For every substance, there is one unique combination of temperature and pressure where all three phases of matter will be at equilibrium. So you will see all three, a solid, a liquid, and a gas at the triple point, at that specific combination of temperature and pressure. The other thing, the other important point is over here. This is called the critical point. It's the highest temperature at which the liquid phase can exist, or it's the combination of temperature and pressure, the highest one at which a liquid can exist. If you exceed the critical point, if you go up here, okay, then you get something called a supercritical fluid. You may or may not have heard of supercritical fluids before, but if something gets to be a supercritical fluid, that state of matter has properties intermediate between a liquid and a gas. And what's really neat about it is, though, that things that are supercritical fluids usually have different solvent properties than they do as a pure liquid. One of the big advances right now in dry cleaning is actually the use of supercritical carbon dioxide to dry clean garments. And if somebody is looking for some sort of minor extra credit and they would like to write me a good reference paper over the break here about how cleaning using, or how supercritical carbon dioxide, so I'll just write down supercritical carbon dioxide is being used right now in chemistry, that would qualify for some good, decent, moderate extra credit, okay? So yeah, that's what a phase diagram shows. There's going to be a couple of problems you guys have for homework dealing with phase diagrams that should elucidate some more features for you. But one more thing I want to point out, just because it happens to show up on the AP test a whole lot, is we're going to compare right here on the left. I've got the phase diagram for dihydrogen monoxide, good old H2O, and over here we have carbon dioxide. Now, if you compare these two, you will see that they have a different triple point. Obviously, they have different temperatures at which they're going to boil. They have different temperatures at which they're going to sublime and change into a solid and whatever. Okay, but what I want to look at right here is this line right here. Now, if you look at water's graph, it goes backwards. The slope is negative. Okay, so the slope is negative. Over here, for carbon dioxide, if you look at that turkey right there, the slope is positive. That tells us something about the nature of the substance, okay? Excuse me. If you have something like this where the slope is positive, what that means is that the solid phase is more dense than the liquid phase. If you have something like this, like you see in water, we have the backward sloping line there on the phase diagram. That tells you that the liquid phase is more dense than the solid phase, or in other words, that the solid will float on the liquid. And you guys already know that from real life, that ice is less dense than liquid water because ice floats in water. So you guys already knew that. So what this tells you is that water expands when it freezes, and carbon dioxide contracts and becomes more dense. So just carry that little tidbit of information with you. Okay, guys. At this time, it is time, I think, to talk about homework. So here's let me give you the problems here really fast. For this podcast, guys, here are the problems you're going to do. This is going to be Chapter 13, Assignment 2. And this is going to be problems number 32 to 35. 37 to 41, and problems 56 to 59. Again, these are not really that difficult, but some of these involve calculations with phase changes, which you'll have to think back to Chapter 6. It's a good review since we have the final exam coming up. It's good stuff if you go back and think about how to calculate a heat change for vaporization, a heat change for something freezing or melting, a heat change for a temperature change, all that good stuff. So those are the problems, guys. Good luck. If you find yourself in dire straits, you can email me, but I don't know how many times I'll check my email. And it's kind of hard to answer questions of this nature over the break anyhow, but I will do my best. So I hope you guys are having a good time. I will see you guys in about a week or so. Have a nice time. Until next time.